Welcome back to ECE 320A. We are, if you're keeping score, we are walking through some of these topics that we're planning to provide information for before the end of the semester. We've done Laplace, we've done convolution. Obviously, there's additional material or resources available for you. You can see that Laplace is units 5, 6, 7, and 9. 9 is sort of matching a lot of these concepts together, or pairing these concepts together. After today's class, I think 9 will make more sense, and today's class is dealing with Unit 10 material, which is Bode plot material. The convolution material you will find in Unit 8, and I'm trying to organize these on the course website as we go. So if you just scroll down sequentially, you should start to see these units and lectures available to you as we cover them or provide information for those. Today I want to go over mainly, I want to really spend most of the time just stepping through some example Bode plots. I don't know that I have time to step through very methodically the different types of basic systems that we could then look at. So I'm going to just combine a couple of types into multiple transfer functions and talk my way through that. You can go back and fill in maybe the details from the unit, whatever I just said, Unit 10 material for Bode plots. Bode plots, another way of saying that is just frequency response plots. We're plotting magnitude and angle of a system, of a transfer function, with respect to frequency. And these are done on semi-log plots, which means we have just a linear axis on the vertical and a logarithmic axis for frequency. That allows us to collect more data horizontally, and it allows for straight line approximations since we're now covering log omega and not the linear omega. The other thing that I might inject occasionally is octave versus a decade. An octave, I'm thinking you're thinking, oh, there's 8 notes in an octave, but in terms of what we want to remember, an octave is a factor of 2. A decade is a factor of 10. So if I say what's happening an octave from here, and here is omega equal to 4, then you would say, oh, what's happening at omega equal 2 times 4 or at 8? Whereas if I say what's happening a decade from this location, if it's bigger, then it's a factor of 10. So if we were looking at omega equal to 10, and I said what's happening a decade higher in frequency, we're now up to 100. And that's the same linear spacing or distance on your paper as from 100 to 1,000 and 1,000 to 10,000, etc. We will focus on minimum phase systems. Minimum phase systems just means that all of the poles and zeros are in the left half of the complex S-plane. And I might abbreviate that LHP. That just saves you when you're texting this information. You just have to say LHP instead of typing out left half S-plane. But here's a picture that maybe helps you recall that. Here's the distinction. All it takes is one pole or 1 zero. Usually you have a non-minimum phase 0, and that actually makes your system a little more challenging in terms of behavior, controlling it, etc. But we will be drawing these or developing these straight line approximations assuming we are playing with minimum phase systems. All poles and zeros in the left half plane. You can draw Bode plots for non-minimum phase systems. You just have to know which of these singularities, pole or zero, are in the right half plane.
What about poles and zeros on the axis?
So poles and zeros on the imaginary axis we're going to allow. We will allow poles and zeros on the imaginary axis, and for steady state accuracy purposes in a controls environment, we might like to put some poles at the origin or pole at the origin. So there's reasons to have, and some systems naturally have a right half plane zero. How many rode a bike in to class today? That has a right half plane zero, your bicycle, in terms of its dynamics. But you can still stabilize the system, and it can still be stabilized. We're just going to focus on sketching these for minimum phase systems. Why do we, so here's the intro and the motivation. Why are we doing this? Is it just a rite of passage? We have to be able to sketch a Bode plot? No. You can have MATLAB sketch it, but it's really nice to know what you're expecting MATLAB to produce, or if you're designing something, knowing why you have something happening in a particular way in the Bode plot. And that's what you'll hopefully start to develop as we go through. I don't expect you to understand all of these useful fours. I'm just trying to tell you that these application areas exist, and there are reasons for having a frequency response or knowing the frequency response of a system. In controls, you can play with a lot of information just from the Bode plots. You can determine a system's stability. You can say, how is it going to behave? If I now kick this system, how is it going to respond? Or if I now say, oh, follow, I'm now maybe in a car and I say, follow 10 degrees, how close is it going to track that 10-degree set point that I want it to follow? That's the steady state accuracy. Filter design. When you're designing, we've already looked at different types of filters, low pass, high pass, and we've described those or thought about those relative to the magnitude behavior of that filter. What's it doing at certain frequency ranges? Is it rolling off? Is it constant? That's what we will learn or understand or become more comfortable with once we know Bode plots. System response. And this one, I'll try to give you more information on this, but if you have a periodic signal, you can now describe that periodic signal with a collection of sines and cosines. Which means if you know how your system is responding to each of these cosines or sines, you can add them all up. If it's a linear system, you can use superposition, and how they respond to those sinusoids you can determine from your frequency response or from the Bode plot. Here's what we're going to try to end up with, are these red lines. How do we figure out how to sketch these red lines on a magnitude plot and a phase plot? When you hear Bode plot, it doesn't just mean one or the other. It means in combination the magnitude and the phase. And if it's minimum phase, you actually just need one or the other, and you can draw the other one. That's one of the reasons why it's nice to first understand what's happening with minimum phase systems. Here's your fallback thinking. If somebody says, oh, what's the Bode plot or what's happening, just pull out a piece of paper or a napkin and sketch the complex S-plane and put your poles and zeros on your complex plane. What are we doing? Then we're just walking up the imaginary axis and evaluating how each of these poles and zeros contribute to the magnitude and angle at that frequency. I've illustrated one. I have 3 dots. That's the walking steps that we're taking. But at omega 1, at frequency omega 1, now we see that that first pole contributes a certain distance or length, and that magnitude is down in the denominator. So we're dividing by that. The second pole contributes a little longer length for that same frequency. That additional length is labeled L sub 2 in this diagram. And that goes in the denominator as well. If you now find those lengths and multiply and divide appropriately, you now know how the system responds to a sinusoid at a frequency of omega 1. You now know, let's say that that result, that magnitude, ends up being 1/2. Then if you inject cosine omega 1t as an input into the system, what you will see in the steady state is 1, that's the magnitude of the input, times that g of j omega's magnitude, which was 1/2. So your output is only going to be half as high as your input. What's the phase relationship? If you're in phase, the peaks align and the troughs align. If you're out of phase, if there's a phase shift, then the peaks and valleys are not all, they won't be aligned. The phase shift tells us how that will be related. In this case, the angle of the first pole you could physically measure. You could, if you've sketched this plot accurately on your complex S-plane, you could get out your protractor and measure that angle theta 1. Or you could do it with your calculator. You could say, oh, it's the inverse tangent of the vertical distance, which is omega 1, divided by the horizontal distance, which is P1. That's now theta 1. Theta 2 determined similarly. Now you have those two angles that those two poles contribute. They're in the denominator, so when you pull them upstairs, they're going to be subtracted. And in this case, we don't have any angle, we don't have a sign, S-I-G-N, in the numerator. We just have a constant, so it has 0 degrees. We have 0 degrees minus the angles of those two poles. This is maybe a lot of information, but we'll start to methodically step through this. But again, this is your fallback thinking. You could say, oh, I've sketched this Bode plot. I wonder if it's even close. You could then pick a couple of points on the imaginary axis and say, does my magnitude seem to match what I'm getting here at these two frequencies? And if it does, then maybe your plot is close. And our straight line approximation is going to be just that. It's an approximation, but it's a quick way to figure things out as far as what's going to happen. 3 problems you want to be comfortable with. First one is the big one, and that's what we're going to go over mostly today, if not the only thing that we get through. And we won't get through all of the details, but given a transfer function, can you now sketch the magnitude and phase plots? Yes. What was K? K was just a number, 3, 5. It's just a gain. It's just a magnitude or a value. So here, K is just a constant. It's a number. And that would influence the magnitude of g of j omega 1. You would have K, if that's 5, divided by, let's say the first pole distance, or L1 is 5, make my job easier, and L2 is 10, you would have 5 divided by 5 times the quantity, 5 times 10, or 1/10 would be the magnitude of G. K is an unspecified constant for a given transfer function. That will be some numerical value. You could be asked the inverse problem, and this is system identification. Somebody might hand you a Bode plot and they say, can you give me the transfer function? Now, based on what we will learn, we'll be able to say, oh, there's a pole at this frequency. Oh, there's another pole at this frequency. There's a 0 here. And we can put all of that information together to actually identify the system or the plant or the circuit, whatever G of S represents. The third problem is, suppose we now have a system, G of S, a transfer function, and we shake it with a given sinusoidal input. It's a linear system, so what do you know the output is going to do in the steady state? If you shake a linear system at 10 radians per second, what are you going to see the output doing? Is it going to be a constant? Is it going to go to 0? It's going to shake. And how will it shake? With exactly the same frequency as the input frequency. So you'll see in the output something at 10 radians per second. And in the steady state, that's what the SS means. In the sinusoidal steady state, your amplitude will be influenced by G as well as your angle. And in fact, it works out, and this is in some of the other material that's available to you. You can, and it's in your book, I'm pretty sure, you can now do the inverse Laplace transform if you wanted to on capital X of S times G of S and examine capital Y of S and say, oh, most of this is transient behavior. I'm not worried about that. What's the steady state terms, or what do they produce? And you can see, or you can derive, that in fact the amplitude of your input is altered or modified by the system at that particular frequency 10. And that's what we were talking about in this plot when we were measuring with the distances from those poles to that frequency. In this case, it's 10. And the phase, we were measuring those angles at that frequency. We combine all of those and find the phase of G of J10, and we can put it into the argument of our output's cosine waveform. We now know more definitively what the output is doing relative to the input in the sinusoidal steady state. That angle just tells you how you're shifted in terms of how are the peaks non-aligned, and the amplitude says how you've now collapsed or expanded the sinusoid at that particular frequency. So let's start plotting. Suppose now we have G1 of S given as 5 over S plus 10. And I may or may not, I don't know how much information I will give you occasionally, but let's just see what we... If I'm doing the Bode plot, then I'm doing the magnitude plot and the phase plot. And the magnitude plot will be in units of dB, so we are looking at the log base 10 of G of J omega times 20. And we're sketching that versus frequency, where the frequency axis is log of omega. The phase is just the angle of all the different pieces. In this particular case, we're looking at the angle of the real number 5 and the angle of j omega plus 10 as omega varies from the origin, 0, up to infinity as we walk up along the imaginary axis. And in fact, since we know that these angles are in effect e to the j angle, what's in the denominator can actually be subtracted from what's in the numerator as terms of its angle. And this is now the angle of 5 minus the angle of j omega plus 10. What's the angle of 5? Now what I'm asking is if I'm in the S-plane, in the complex S-plane, and I was at a point 5, at a location of value 5, what's the angle that makes with the positive real axis? Now you're standing at the origin and you look over at 5 and you say, okay, what angle am I having to move through in terms of my eyes or body to get to that point? There's no angle. It's 0. So that is, and the other one, we have a pole over here at minus 10. Now as we change omega, there's the angle at omega 1, and we could evaluate that, and since it's in the denominator, we are actually subtracting that in our sketch. So let's now look at what we have. We now have g sub 1 of j omega. We're replacing, now we're focusing on the behavior of this transfer function on the imaginary axis. That's the Bode plot. That's the frequency response. And the other thing that we want to do to make our life more consistent in terms of the sketching process is let's convert this transfer function, which right now I would say this is in pole 0 form. You can see that the factors are explicitly identifying the poles and the zeros. We just have one factor, and it's a pole factor. We have a constant of 5, but for Bode plots, it's more consistent to factor that into time constant form, which really just means, oh, if I have a constant here in my linear factor, I want to factor that out and make that constant 1. I now factor out the 10. And I now have that for my transfer function. I haven't changed anything. I've just reparameterized it. I can move the 10 in the denominator upstairs. And in this case, my K, my capital K from before, is this 1/2. And because I've put everything into time constant forms, that gain doesn't change when I look at omega equal to 0. Because then I just have the 1 in the denominator, and I'll have 1s in all my other factors if I've put them all in time constant form. And now I can more convincingly say, oh, my gain is 1/2 relative to how I'm sketching this diagram. Now, if we look at the magnitude of G in dB, we now have 20 log base 10 of 1/2 over j omega over 10 plus 1. One of the reasons why we're doing this in a dB scale is so that multiplications and divisions can just be additions and subtractions because of the logarithm. this can now be rewritten as 20 log of 1/2. I don't even have to worry about the magnitude of that since it's positive, minus 20 log of the magnitude of j omega over 10 plus 1. Hopefully you can see that this particular term doesn't depend on omega. It's constant. That will be a given contribution to our overall Bode plot for all omega. This is constant. And this one is now the one that varies as a function of omega. But what we're going to do is now we're going to just recite some fairy tales. Goldilocks. Goldilocks did what? Things were maybe a little cold, a little hot, or just right. Well, now that's the way we're going to treat these factors. They're going to be a little small, a little big, just right. The Goldilocks point. And all of these are based on decades away from your break frequency. We will look at that argument on the second term and say, can we approximate that? And we'll say, well, for small values, so now we're saying, let's just try to sketch. Do you see the first term's not going to be hard to sketch? We just say 20 log of 1/2, and that's going to be contributing that amount of gain over all frequencies. And what is that? 20 log of 1/2. You could even invoke the logarithm property again and say, oh, that's 20 log of 1. So now we could say, oh, this is 20 log of 1 minus 20 log of 2. That's this. And what's log of 1? 0. So this one now is 0. And what's log of 2? Anybody know what 2 logs represent? Log of 1 you told me was 0. What's log of 10? 1. So we know we're between 0 and 1, right? And it wouldn't be a bad thing on the final, if you wanted to, you could bring in, I think I'm going to allow you probably a crib sheet to just have, here's omega and here's log of omega, and just do that from 1 to 10. Log of 2 ends up being 0.3, roughly. Yes. There'll probably be calculators allowed, but you may want, you don't want to do I don't want to do log of 2 on my calculator. I want to know that, or just be able to refer and say, oh, that's 0.3. Just saying, okay, you feel comfortable plugging it into your calculator, that's fine. But it's very instructional and actually very, comforting maybe, to just make that chart physically and say what's omega, or what's the frequency and what's log of omega. Just saying. So then you can see what happens at log of 2, log of 3, log of 4, and then it's easier to quickly sketch these. Now if somebody says, oh, this pole is at 20, then you go on your semi-log axis, which is between 10 and 100, and you go, where am I if I'm log of 20? Where am I between 10 and 100? I'm not this linear distance at 20. I'm now 30% of the distance between 10 and 100. So now 20 is 30% of the distance. Maybe I should do it this way. 20 is now 30% of the way towards 100 on a semi-log, on a logarithmic axis. Helps your sketching. Okay? Anyway, this is now 0.3, and all of this together is now minus 6 dB. Whatever happens elsewhere in this sketch, if we said, oh, forget the constant for now, you could sketch everything and then say, oh, I need to introduce the constant's contribution. You would just shift your entire magnitude curve down by 6 dB everywhere. It just shifts everything down. Now, let's see what we need to shift in terms of shifting down. We need to get back to Goldilocks. We now are trying to sketch that. And it has a minus sign. Why did it end up with a minus sign? It was a pole factor. It was in the denominator. It was downstairs. Things are going to be going down because of that pole factor, the negative. So our slopes are negative. But we now want to focus on straight line approximations. So that now if we're looking at this expression, j omega over 10 plus 1, and here when you go home tonight and you're redoing this from memory, not with your calculator, you replace 10 with an omega, and you just start saying, okay, what's going to happen for small omega? What is omega naught? Well, in this case, it's 10. But now I'm saying I want to look at the small omega case. What do I mean by small omega? Well, I want this to be approximately 1. And when is that going to happen? Well, that's what I'm going to, here's our approximation. We're going to say that it's approximately 1 when we have the imaginary component, which is omega over omega naught, which in this case is 10, is less than or much less than 1, and what we are agreeing to is that we will say, oh, we need omega over 10 to be 0.1. 0.1 is much less than 1. That's our Goldilocks value. If we are now saying we are going to approximate this magnitude of j omega over 10 plus 1 when we have small frequencies with 1, what's a small frequency? Well, it's a decade before the break frequency. That's the 0.1. So this is now when omega is less than 0.1 times 10. Here is the decade before. In our case, that means 1. Up until omega equal to 1, we're just going to replace that magnitude as if it was just 1. And log of 1 is 0. So now we're just going to go 0 dB until at least we get to omega equal to 1. Let's now do the same thing for the big chair or the large frequency. Now we want the imaginary component to dominate. And when is that going to happen? Well, if we use a similar thought process, we would say this needs to be much bigger than 1. Oh, well then we need omega over 10 to be bigger than 10. We're comparing it to 1. That's why we put it in time constant form. That's why we do that, so that now we always are just talking about a decade before and a decade after a given break frequency. That's why I said when you go home, replace the 10 with an omega naught. And then this is true in general for a given linear factor. In this case, we now say, oh, we want omega to be bigger than 10 times 10, and this is now our decade after the break. Here's omega naught, and there's omega naught. So if we were looking at this, if we said, oh, at omega a factor of 10 or a decade bigger than our break, what is in fact happening to 20 log base 10 of j omega over 10? What's the magnitude of j? If I said we now have this playing field, which is the complex plane, I want you to go and stand on j. I hope no one in here has the name j. We're not standing on j. We're standing on the location j in the complex plane. Where is that? Horizontal, vertical. Vertical, and how far away from the origin? 1. So the magnitude of j is 1. We can get rid of that j in the j omega over 10. We can now say, oh, this is in fact 20 log of omega over 10. And if we're just dealing with positive omegas, we really don't need to worry about the absolute value sign anymore. And we can say, oh, this is now 20 log of omega minus 20 log of 10. And now do you see you have a constant piece and a piece that varies with log of omega? And what are we sketching this with respect to? What's our x? Log of omega. And I didn't show, but before this is that negative sign. So this term really has a minus 20 log of omega. We're sloping at minus 20 log of omega, or minus 20x. That's why when we have a single pole factor, we're going down at 20 dB per decade. The right-hand side just tells us, oh, when would this slope actually occur? When is this different from 0? Our straight line for small frequencies was saying you're just at 0 dB. And now we said, oh, for big frequencies, we're sloping at minus 20 dB per decade. When do those two straight line approximations match? When this piece is equal to 0. And what value of omega will cause that to be true? When omega is 10, the break frequency. So now, this will be 0 dB when omega is equal to 10. And in fact, now we've basically sketched our magnitude Bode plot. Did everybody sketch that already? Or are you plugging it into your calculator? You could have it in your calculator, maybe. Probably you do have. But now and I am kind of picking on. I hope you know that I'm not meaning anything by that, right? Don't go to my boss and complain. I'll just be the boss that day. You can complain to me, huh? So here's 10, here's 1, here's 10 to the minus 1, here's 10, there's 100. Well, let's just label this as log of omega. And this is going to be our magnitude of g, of j omega. This is 1 in dB. If I just plotted this pole factor, if I didn't worry about the constant piece, the 20 log of 1/2, how would I sketch that on this axis? How would I sketch the magnitude of g sub 1 of j omega in dB? Straight line approximation. What am I focusing on here. Another reason for writing it in time constant form. Now you're focusing on that break frequency of 10. That's where things happen. Much bigger than that, you're sloping. Smaller than that, you're 0 dB. So now we are 0 dB, if I now label this as 0 dB, until we hit 10. And after 10, now we're going down with a slope, because it's just one of these factors, 20 dB per decade. So if I just say this is 20 dB and this is now 40 dB, I would just connect those dots, and it doesn't look like my dots were spaced right, so I'll just say that's my how do I make this the actual, well, how do I incorporate the other term? This right now is the pole factor's contribution to the magnitude. I haven't yet introduced the gain, but the gain was just minus 6 dB. That just shifts everything down by 6 dB. And if you wanted to, you could say, well, let me draw all of these curves by themselves. Let's say this is now 6 dB. You would now just add these up point for point, because now we are sketching these for decibels, and we can add those. So now I have 0 and minus 6. I'm right there. 0 and minus 6. So I'm minus 6 until I get to 10. And then I'm sloping parallel to that pole factor by itself, and I'm underneath that by 6 dB. But the slope is still the same. That's minus 20 dB per decade. You've now sketched the magnitude of your Bode plot. Yes? So where did the minus 20 log 10 go? This was now, if you just sketched 20 log of omega, you would now, when would 20 log of omega be 0? When omega is 1. So now that allows us to actually delay, in a sense, where we start falling off. So now you really don't have to worry so much about that in plotting these. You just say, where's my pole, or where's my 0? I'm now going to be sloping at 20 dB down or up, if it's a pole or a 0, based on where that break occurred. But that particular additional term is just accounting for where that happens. But if you know where it happens, which in this case is 10, we just go relative to 10 and go down in this case because it was a pole factor. So that question, I think, was what happened to that? Well, it's accounting for the fact that we're not sloping here. We're actually starting our slope right there at 10. But we don't even really have to keep track of all of those details. We just say, where are our poles and zeros? Let me just start making my slope changes at those locations. Let's look at the phase. So now the phase, again, it's guided a little bit by, so let me just Goldilocks. And we are marching up this axis. Where would we be on that j omega axis a decade before 10? In terms of j omega, and I said, okay, j omega, what's omega value-wise a decade before 10. 0.1 times 10. It's at 1. If we walked up that axis to J1, let's say that's right here, what we are agreeing to now in this straight line approximation is, oh, that angle, forget it. It's 0. Any frequencies before that, we're just going to say its angular contribution is 0 because it's small. What is a decade beyond 10? It's at 100, so do you see my scale is way off? I'd have to be way up here. But if I now said this is J100, what's this angle? It's pretty big. It's getting close to 90. It's not quite there, but we're just going to approximate it as 90. What's the biggest angle we could ever get from that pole? 90. We can only go to infinity, and we can only obtain a right triangle. So now that one pole factor only contributes 0 to 90 degrees of angle. And since it's in the denominator, we'll actually be subtracting these contributions. And what have we done? We've played Goldilocks again. We said, what's small? Oh, it's a decade before the break. What's big? A decade after the break. We now know that this angle of 90 degrees is distributed across a 2-decade span centered at the break frequency. And we're just going to make it a straight line contribution between 0, and since it's a pole, it's minus 90. And we'll just draw a straight line. Once we get to minus 90 at 100, we say there's no more angle contribution. It's just going to be minus 90 from that point forward. We've now sketched our phase plot for G sub 1. G sub 1, whoops, I said phase, kind of like the triangle and rectangle from before. Sorry. But if you're now sketching these, you would align your frequency axis so that now this is 10, this is 1, and let's just say that this point is minus 90 degrees. Now we said, oh, find a decade before our break, that's 1. Find a decade after, that's 100. And we know that now we're at minus 90 here, and we're at 0 degrees here. Let's now just connect those. And what would, in fact, be our angle at J10? Up 10 over 10, 45 degrees, and that's what our straight line produces. It gives us our midpoint, the Goldilocks point for our angle at the break. So right at the break, this linear factor contributes 45 degrees. Since it's downstairs, it's minus 45 degrees. Do we need to worry about the constant? The 1/2, the K, in this phase plot. What's the angle of 1/2? What's the angle of a number 1/2? 0 degrees. We're looking at 1/2 in the complex plane, and we say, well, there's no angle that I have to turn through to get to that real value. This is all there is then to that plot. We now know the magnitude and phase for G sub 1. And if somebody says, how's this system going to shake at 100 radians per second? You can now tell them. You can say, oh, the phase is going to be minus 90 degrees. So here's the phase, G1 of J100. And the magnitude is right there. And that's going to be at minus 26 dB, and you would have to then convert that to an actual numerical value from dB, but you would just say, oh, 20 log of some number, A, is equal to minus 26, and solve for A. And that would be the scale factor. What I'm saying now is, if this is now G1 of J100 in dB, we've said that's minus 26 dB. If we now have minus 26 dB, and that's minus 20 log base 10 of some scale factor A, and we solve for A. Divide both sides by 20. And now we have, let me see. We just want it to be in dB, so that's 20 log of A. Now we have log base 10 of A is now equal to minus 26 over 20. And how do we take the anti-log base 10? We just raise everything to the power 10. And that would now be how we would scale. This would be the numerical value, not in dB. This would be G of J100 in absolute number. Let's sketch another Bode plot, because I know you want to run home. Well, now running, you might be running because of the rain, but I'm thinking you want to run to get home quick so you can do this. This is now, let's say, our second example. Let's say this is G sub 2 of S is now 10S over S plus 1, S plus 100. Bless you. What's the first thing you want to do if you're now sketching the Bode plot of this? This is presently in pole zero form. We now want to normalize all of those constants to 1. We want to put it in time constant form, and I'm going to be very specific in that first one. I'm going to factor out a 1 and say, oh, that's S over 1 plus 1, so that I know exactly where my pole is. It's underneath the S. It's 1. The other one, and I now have 10S. And I'm sketching this for, or on the imaginary axis. I now have 10 divided by 100 for my gain term, or 0.1. I have j omega, a j omega factor. That's a 0 at the origin. It's on the imaginary axis. And then I have the two pole factors, j omega over 1 plus 1 and j omega over 100 plus 1. Now, somebody might put this into MATLAB and say, I don't care what Tharp was doing, I can just do this in MATLAB. So you do this in MATLAB and you give it to a friend and they go, I don't know what you did, but you must have entered something wrong. So now you're checking some extreme values. I might say, oh, what's the phase of this Bode plot at small frequencies? What's this transfer function's phase at small frequencies? One, you have to figure out what does he mean by small, and what is the phase at that frequency. What would you think small represents? Is it an absolute number? Oh, anything less than 1. That was maybe a poor choice of numbers in the beginning example. Anything less than 1 is small. No, because you might have a transfer function that's doing all of its activity at poles and zeros, 0.001, 0.02, etc. Very small. So what do we consider small for a generic transfer function? You would look at all of your breaks, all of your poles and zeros, and you go, let me go a decade below the smallest one. And that's going to be my small. You do the same thing for large, and you say, oh, let me find all my poles and zeros, let me go to the biggest one, and then I'm going to go a decade beyond that and say, oh, here are my frequencies that I'm considering big or high. Clear on that? What's the phase of this transfer function for small frequencies? What's small frequency for this particular example? 0.1. We actually have a 0 at the origin that's always on in terms of its magnitude behavior. But the breaks, we just have 2 breaks. The poles and zeros at the origin are always sloping in their magnitude contribution. The breaks, the changes in slopes, are just going to be at 1 and 100. Here we would say, oh, a decade before 1 at 0.1. So anything below 0.1 would be small for this system. We would say, okay, what's the phase? Well, what's the phase contribution of this first pole factor at 0.1 that we've agreed to? 0. How much phase is the second factor contributing at 0.1 omega? 0. The only thing that's contributing angle is that 0 at the origin. And it contributes angle all the time because it's stuck. It's j omega. It's always what? It's always j. And what is j? Now you know how far away it is from the origin. It's 1. We said go stand on j. Now if you had to turn towards j, what angle would you turn through? If here's j in seat number 6, and I'm 1 unit away, and here's the real axis, I've turned through the angle to get to j. What did I turn through? A right angle, 90 degrees. That 0 factor is contributing 90 degrees all the time. And since it's upstairs, it's plus 90. And we just said that the bottoms aren't contributing anything. So what's the angle? What's the phase of this transfer function at small frequencies? 90 degrees. Do you see how you arrived at that? And you didn't even have to use your calculator. You just have to look at that transfer function and you go, got it. What's the phase at high frequencies? What's high? This is a non-smoking campus. Medical. What's a large frequency? Pardon? A decade beyond 100. 1,000, right? So above 1,000, we're large. We're not high in this class. We're high on learning. Okay? What angle is that first pole factor contributing at 1,000? Omega equal to 1,000. That first pole factor, what angle is it contributing? Now get out your complex plane. If it's not making sense, you put a pole at -10 and you go, okay, I'm going to walk up the imaginary axis until I reach J 1,000. What's the angle that that pole gives me? Oh, 90 degrees, but I'm downstairs. It's a -90. What's the 0 giving me? +90 all the time. Once I've reached 1,000 radians per second, that first pole factor has canceled the angle due to the 0. But I have another pole factor. What angle is it giving me? Since we're a decade beyond where it broke, we're straight lining this. We're saying it's giving me 90 degrees, and since it's downstairs, it's -90. What's the phase of this transfer function at large frequencies? 90, -90, -90, -90. And now they give you a Bode plot. Your friend hands you a Bode plot, and that Bode plot at high frequencies was 0 degrees. And you go back, figure it out. You did something wrong. How'd you know? Why? You can explain, right? How that you said, well, I looked at your phase plot, and it was not giving me -90 degrees at large frequencies, so I knew something was wrong. Clear? Or maybe the phase curve was starting at 0 degrees at low frequencies. Where was it supposed to begin? Where the 0 was contributing, it was giving us 90 degrees. And what's another way of checking this? Now the magnitude curve, you say your magnitude curve's off too. What's the slope at high frequencies of the magnitude curve? Is it even sloping? How much is the magnitude curve sloping at high frequencies? So what's producing slope? We have how many factors? We have a constant factor of 0.1. That's always just flat, isn't it? What's log of 0.1? -1 times 20, so that's giving us -20 dB all the time. Then we have a 0 factor at the origin. What does that give us? That's now coming up from the bottom and going up all the time, plus 20 dB per decade. If we took 20 log of j omega, that's just 20 log of omega, and we're plotting with respect to log of omega. So that goes up and it crosses where? 0 dB at what frequency? And now we're pinning the 0 curve on we're at the party. We're high on education. And we've now pinned that, and it's sloping this way, isn't it? We've pinned it where? 0 dB at what frequency? Log of what gives me 0? Log of 1 gives me 0. So at omega equal to 1 is where we can pin that particular factor's magnitude plot. And it's always sloping, plus 20 dB. What do these pole factors produce at large frequencies? They each contribute individually 20 dB down per decade. We had 20 up from the 0 always. Then at 1, we start going down at 20 dB per decade. Now we're flat, our slope. We're flat until we reach the last pole at 100, its break, and it goes down at 20 dB per decade. What's our slope in magnitude at high frequencies? minus 20 dB per decade. And they give you a Bode plot and it's flat at low frequencies. Is that true for this transfer function? No, you're supposed to be sloping up from the bottom due to that 0 at the origin. Do you see how you can cross-check your calculator or Bode plot generated material with just these extreme questions, or questions at extreme values? And small and large are relative, aren't they? They depend on the poles and zeros that you have. So now can we sketch this Bode plot? Now that we've talked our way through, we now can see, we can now see this Bode plot. You're missing it if you're listening to this, right? A lot's happened between me writing down that time constant form and what we've just gone through. So, if we did this with the magnitude, where do I want to start labeling this? Probably a decade or less, maybe even a little bit less, but we know that the last break is occurring at 1, so we could, yeah, I should have done it at 1 because I'm running out of space. Let me do 1, 0, 1, 2, and 3. This is now log of omega. We said that that constant term was 20 log of 0.1. That's minus 20 dB. We now have minus 20 dB here due to the constant. We have a 0 at the origin. That was sloping up at 20 dB per decade forever. That just keeps going and going, but it crosses, here's my 0 dB line, through. Guys, wake me up. Oh, man. Obviously, I'm in the high frequency range here. Oh. Why do I have to correct? I was doing some, ooh, I don't want to do that. I was going through 10, let's see what happens, okay. And not through 1. So now I need to do this for my zero at the origin. Is that better or is it worse? That's going through 0 dB at omega equal to 1 with a slope of plus 20 dB per decade. Then we have the first pole factor. It also starts right here, but it was 0 until it reaches its break, and then it goes down at minus 20 dB. This is the pole at omega equal to 1. And then we had another pole at omega equal to 100. And it's now sloping down at 20 dB per decade. We now simply start far enough to the left, far enough in low frequencies. Maybe I should do this for you guys. And then work our way across, trying to incorporate all of the different breaks and slopes as we go. which means that we would start here if we didn't have that constant contribution. We now have to actually start 20 dB below that because the constant is giving us 20 dB. And you can go back to, let's say, this point right here. That point right there has 20 dB, minus 20 dB from the constant and minus 20 dB from the 0 at the origin. So I should be at minus 40 dB net. I'm coming up until where? Until I reach that first slope change, which is at the first pole, and that's occurring at 1, and this is supposed to be a straight line, but that's now right at my 0 at the origin gives me 0 dB at that point. My constant gives me minus 20. That's the only thing working at that point. I should be at minus 20 dB at that frequency. Now what do I do? This is plus 20 dB per decade. Now what do I do with the red line? I had plus 20 and minus 20 for slopes. They cancel. Now what do I do at 10? Nothing has happened. Nothing has been introduced. I've already introduced that that pole at omega equal to 1. I'm going flat until I get my next break, which happened at 100. And at that point, I now just go 20 dB down. And that's my magnitude plot. What's my phase plot look like? I just need a cheat sheet here. So I have this. And I want to know what's my phase look like. I have 90 degrees due to the 0 at the origin. Always. Then I have to worry about turning on and turning off the slopes due to these linear factors. They're both contributing eventually minus 90 degrees. The first one is contributing its slope change spread over 2 decades, centered around the break. It breaks at 1. I now should be seeing that first factor, and I might say, oh, I'm going to go down there and I'm going to come back up here, just as sort of guides. And eventually I'm going to be down here at minus 90. And I can just connect those dots. That's due to the first pole factor at 1. The second one is centered around 100. So it starts contributing phase a decade before that, and it stops contributing phase a decade after that. Should I do a different color? So now that second one is in green, if you can see that. It's now starting its contribution of phase a decade before the break, and it finishes and keeps at minus 90 a decade after. Now I just have to add everything up. And that just says start low enough in frequencies. So I start at 90 degrees, and then I start sloping down. And at 10, I have minus 90 from the pole and plus 90 from the 0. I should be at 0. What do I do now? Now the pole factor at 1 is done contributing, so it's now canceled the 0 factor. All I'm left with really is the green curve. And is that consistent with what we had argued before? We start low frequencies, a phase of plus 90. At high frequencies, eventually we get to minus 90. Yes? Correct. The 0 at the origin, or if you had a pole at the origin, a pole at the origin would always contribute minus 90 degrees. A 0 at the origin is always plus 90 degrees, and you don't have to worry about it starting and stopping. The phase curve is more challenging to draw because you have to turn them on and turn them off in terms of slopes. The magnitudes, once you start sloping, it's always sloping. Either pole or 0, unless what? Unless you're pinning a pole or 0 at the origin, then they're always on. You don't even have to worry about when they start. You just have to make sure you put it in the right spot initially. We'll pick up there somewhere next week.